Alright, so 4.7 is what's called optimization problems. It's another one of those really great sections that shows you the application of the derivatives and what you've been doing with the derivatives up to now. Now, what we're going to do is I'm going to give you an entryway into optimization problems, which back in my day were called max-min, or perhaps that was just my teacher. But basically these are the application, sort of the word problem version of what we were doing back in 4.1, which is finding extrema, okay? Maximum and minimum. And you can sort of see how this might actually be helpful when you are doing some sort of engineering project and you need to figure out how to maximize the efficiency of a factory or minimize the cost of this, that, or the other when there are certain constraints involved. Now, of course, compared to the ridiculous calculations that those deal with, this is Mickey Mouse. But we have to learn to crawl before we can walk. So this should be rather straightforward. Let's go ahead and jump in with an example that we have actually seen already. This is a problem that I gave you back in Algebra 2, and I did it very intentionally because I wanted to come back to it when we got to calculus. And just because I'm not there doesn't mean we're not going to do it. Now, if you have a right triangle, and this is a right triangle, if we have a right triangle that is 3 by 4 along the legs, and let's say you want to inscribe a rectangle, okay? Let's say you want to inscribe a rectangle, and of course that's just one example of where the rectangle could be. It could be very short and long down here, it could be very tall and narrow and up here. But I just need to go ahead and draw a rectangle so that I can actually use this right here. Now, what is the largest rectangle that I can actually inscribe within that right triangle? And therein is the problem, okay? Now, some of you may remember this, or at least have some sort of glimmer of recognition on this. We need to go ahead and start assigning variables, okay? So I know that if I'm going to go ahead and say, well, that right there is, let's call that x, okay? Let's call that right there x, okay? And let's, for right now at least, call that y, okay? Now, that means that this over here is 4 minus x, because it's what's left over after you take 4 and subtract x, right? Up here, we have 3 minus y. Now, that's important because this edge over here is also x. This edge over here is also y. And what do we actually see in this? Well, I see the fact that I have another right triangle up here, and I have a third right triangle over here, and all three of those triangles are similar. So I can actually use the proportional sides to actually take one of these variables, either the x or the y, and put it in terms of the other, okay? I know that if I'm going to have 3 to 4, that is the same ratio as y to 4 minus x. It's also the same ratio as 3 minus y to x. You just have to decide which variable you want to get rid of. Well, since we're used to dealing with x, let's get rid of y, okay? And I know that that large triangle gives me a 3 to 4 ratio, whereas this over here gives me a ratio of the same sides of 4 minus x. And then what I want to do is I just want to solve for y. So I have 12 minus 3x is equal to 4y, or 3 minus 3/4 x is equal to y. Now that's going to be pretty important because I'm trying to maximize an area, right? Well, if I'm trying to maximize an area, I need to go ahead and set up that area that I'm maximizing. I need to maximize x, y. The product, right? The area of the rectangle. But now that I have y in terms of x, that is actually that, okay, which becomes negative 3/4 x squared plus 3x. Now, if I want to maximize that, I actually don't need calculus. That is an upside-down parabola. We know how to find the maximum point of an upside-down parabola. We basically just have to find its vertex, okay? Well, let's go ahead and turn it into vertex form. So let's do it the algebra 2 way before we do it the calculus way. We need to go ahead and factor out that leading coefficient, which of course leaves us with x squared. And when I take 3/4 out of here, a negative 3/4, I'm left with 4x. Well, completing that square is actually very easy. That right there is not really a positive 4, it's really a negative 3, so that becomes positive 3 right there. And in vertex form, we have that, okay? Now this is a function of area in terms of x. So when x is 2, the area is maximized at a value of 3. Now, could I have done it the other way, and instead of getting y in terms of x, could I have used the other, I mean, I could have used either triangle, it doesn't really matter, and solved x in terms of y. Sure, and you still would have gotten 3 right here as the maximum area. You just would have gotten y minus something different right there. It wouldn't necessarily have been 2, okay? The fact that it's 2 right there has everything to do with the fact that you got area in terms of x instead of area in terms of y. And actually, when I did this back in Algebra 2 for you guys, we actually did it both ways. We did area in terms of x and then area in terms of y, showing you that you get that same area right there. It's just with respect to a different input variable. Now, that is the way that we maximize the area, find the maximum area of 3, or of course, if the question asks, you know, when is the area maximized, you say, okay, well, when x is equal to 2. And when x is equal to 2, you can obviously plug 2 into here and get the corresponding y value, right? And that's 3/2. Because if you plug in 2, that becomes 3 minus 3/2, which is 3/2. So when x is equal to 2 and y is equal to 3/2, we get a maximum area of 3. Well, let's go ahead and do it using our calculus, okay? So instead of turning that function into vertex form, I'm going to differentiate it. And I get negative 3/2 x plus 3. And then, of course, I need to go ahead and I need to set that equal to 0. Negative 3/2 x plus 3 is equal to 0. And of course, if I push the 3 over to the other side, I get negative 3. Multiply by 2/3, and I get x is equal to 2. When x is equal to 2, I have a horizontal tangent line. And of course, that makes sense because, like I said before, this is an upside-down parabola. But of course, it's quadratic, it's a parabola. That's kind of one of the only ones that we can actually do using our Algebra 2 knowledge. If we go beyond a parabola, we're going to have calculus. But I wanted to sort of enter into optimization with a question that, at least, if you don't remember this question exactly, at least the contours of it should be relatively familiar. And so we know when x is equal to 2, we have a maximum, and then all you have to do in order to find out what that maximum area is just evaluate a of 2. And I get negative 3/4 times 2 squared plus 3 times 2. Well, that's going to be negative 3 plus 6, or positive 3. So when you have a horizontal tangent line, and therefore a critical value at x is equal to 2, you have your maximum value here at a of 2 is equal to 3. Now that is a way of sort of entering in slowly by doing it with a quadratic, which we've actually seen before. Let's go ahead and do something that's a little bit more robust. We're going to go ahead and do a problem that is, you know, one of the classics when it comes to optimization questions. I always like to focus on the classics. Okay, let's go ahead and look here at number 2, and this is, you know, this is just a This is just a worksheet that's widely available on the internet. You could probably find it if you did the right Google search. And it says, a rancher wants to construct 2 identical rectangular corrals using 200 feet of fencing. The rancher decides to build them adjacent to each other, so they share fencing on one side. What dimension should the rancher use to construct each corral so that together they will enclose the largest possible area? Well, if you have a good memory, you're thinking, well, we did one of these in Algebra 2 as well. And you're right, we did, okay? But let's go ahead, and the first thing we need to do is we need to set up the picture, okay? He's using 200 feet of fencing, and he has 2 adjacent rectangular areas, okay? Rectangular corrals. And so what we have here is something like this, okay? Now, there are different ways of setting up the area. I usually like to put X, 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 Y, 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 okay? And therefore, each of the small corrals is X times Y. But the area of the entire thing, right, is 2xy. Well, I'm obviously looking for the largest possible area. I'm looking to maximize this. But I know that this has 3 variables, and so by substitution, I need to get rid of one of them. But you've also been told that all of this fencing is equal to 200 feet. And so you simply need to set the perimeter equal to 200. That would be 4x plus 3y is equal to 200. And you can solve either for x or for y. I'm always in the habit of getting rid of y, since most people usually just have a comfort with x, because that's what we've always worked with. And so I get 3y is equal to 200 minus 4x, or y is equal to 200 minus 4x over 3. Okay, well then I'm going to take this expression and I'm going to plug it in right there for that y value, and that's going to give me a quadratic. And now I know that area is simply in terms of x, so I can call it a of x. So you have 2x, 200 minus 4x over 3. Okay, well that's going to be negative 4/3 x. Okay, negative 4/3 x times 2x is negative 8/3 x squared. Negative 8/3 x squared. Now this right here is 200 over 3. Times 2x is 400 thirds x. 400 thirds x. That is the area of both corrals based upon the information that is given, such that I can actually write it in terms of a single variable. Now what I need to do from here is I need to go ahead and take the derivative, and I get negative 16 thirds x plus 400 thirds. And now of course I need to go ahead and set that equal to 0. Now that doesn't wind up being all that bad, because the moment you set it equal to 0, obviously you can multiply through by 3 over 16 or something like that, okay? And when you multiply by 3 over 16, or negative 3 over 16, you're going to get x minus 25 is equal to 0, or x is equal to 25. That right there is simply the length of that portion right there, that x value, that will make the maximum area. If you want to actually find the maximum area, you then have to go back in and plug back into the original function. And it might, of course, be a little bit easier to do if you have it in terms of, if you have it factored. Factored might actually be easier in order to evaluate the 25, because who the heck wants to, deal with 625 times negative 8/3. But that right there is your x value, which maximizes the area. And if you have your calculator, you just go ahead and plug it in and see that, okay? Now, this could have been done using Algebra 2 skills as well, because that, as nasty as it is just a quadratic, okay? And that quadratic can be put into vertex form. It's a downward facing quadratic, and in vertex form it will reveal its vertex, and therefore it's the x value at which we found a maximum value, and it actually will reveal that maximum value. So just really quickly, let's go ahead. Okay, so if we factor out -8/3, okay, well, 4 can be pulled out of 400. That's relatively easy. Okay, 8 can be pulled out of 400. If you pull 8 out of 400, you wind up getting 50. Okay, and therefore it's minus 50x plus blank, right, in order to complete the square. Well, that winds up being 25, half of that squared, so that winds up being 625. Of course, that's not really a 625. That's really -8/3 times 625. And therefore, this is whatever 625 is times 8/3. And that right there is your maximum value. Okay? Now, that winds up being okay. The great thing about it being a quadratic is you can actually do it both ways and check your answer. The bad part about this is that it only works for quadratics, and therefore if you're going to do anything else, which we're going to here in just a moment, you're going to have to use the calculus method of actually finding the critical values and then evaluating those critical values to find those maximum areas or maximum whatever that you're looking for. Okay? In the next video, we'll go ahead and concentrate on ones that are a little bit more robust, but I hope that was a good introduction. Email me with any questions as per usual.